Welcome to this lecture. This is the third lecture of week 7. In this week, we have been discussing about the equivalent conditions for weak convergence of Borel probability measures on the real line. We have also seen similar conditions stated in terms of the associated random variables. We have further looked at sufficient conditions under special cases of random variables when these random variables are either absolutely continuous or purely discrete, and these sufficient conditions are in terms of the pointwise convergence of the corresponding probability density functions or the probability mass functions respectively. We have also seen the important comments on other properties of weak convergences, specifically that such convergences are metrizable, meaning there is a metric on the collection of probability measures on the real line such that it captures exactly the concept of weak convergence. Now, with this understanding, we now ask the question that whether these ideas of weak convergence that we have considered on the real line can be extended to higher dimensional setting, and in this lecture we are going to discuss exactly that. Without further delay, let us continue discussing using the lecture notes. So, as said earlier, we are going to now talk about weak convergence of Borel probability measures on R D now. So, this is the D dimensional Euclidean space, and whenever we talk about such a convergence, we also get a similar notion of convergence now for D dimensional random vectors. So, before we go forward, we first state certain notations, and then what we are going to see is that whatever results that we have discussed in the one dimensional situation essentially goes through in the D dimensional setting. So, let us state this basic notational scheme that we use in this lecture. So, we start with any point or any vector in the D dimensional Euclidean space R D. So, then any such vector is made up of D components, each of which are now real numbers, and these we typically write in terms of a column vector. So, for notational convenience, we have written it in terms of the transpose of a row vector. Now, given any such point or a vector small x, we can look at this half infinite rectangle, the higher dimensional version of it, given by this, that we look at all the components x 1, x 2 and so on, and for each component look at the corresponding intervals of this type and look at the product of this. So, this is simply the Cartesian product of all these component intervals, and that whole product is going to give us this D dimensional rectangle half infinite. Now, if we take any probability measure mu on the D dimensional Euclidean space together with the Borel sigma field, then we can also talk about the associated distribution function. So, in short we are going to again write df for this. So, here we are going to get this function now defined on R D. So, we have this function f mu defined on R D taking values between 0 and 1, defined in this way that for all points x in R D, you just look at this half infinite rectangle that we have just talked about, look at the measure or probability of such rectangles. So, that value is between 0 and 1, and you associate this value to this point small x through this function f mu. So, that is the associated distribution function of the probability measure mu. Now, if you are talking about a random vector, D dimensional random vector, then again we recall that any such random vector will have D components, each of which are now random variables on their own right, and again our standard notational scheme for such things is to write them in terms of a column vector, but for notational convenience we write it as the transpose of a row vector. Now, suppose this random vector is given to us on some fixed probability space omega f p, then we can again look at the induced measure on R D together with the Borel sigma field. The induced measure, which is now denoted as P compose x inverse, this becomes a probability measure. So, this we also refer to as the law or distribution of this random vector. Now, associated to this probability measure, we can also look at the corresponding distribution function, and for the case of random vectors, we typically refer to such distribution functions as the joint distribution function. So, we write it in terms of f x. So, this is again of course a function defined on R D and takes values between 0 to 1, and the idea is pretty simple, that you take any point or a vector small x in R D and look at p compose x inverse, that probability measure, what is the size or probability that associates to this half infinite rectangle. So, that gives you the corresponding joint distribution function, but you can simplify this further in terms of the pre images of the individual component random variables in this way. So, this is a standard computation which you should be familiar with by now. Now, what we do is that this can be written in our more standard notational setting, that we have to consider this event now involving all these component random variables, that the component random variable x 1 takes the value less or equal to x 1 and so on. So, that is the event that we are looking at, and the probability of that exactly gives us the corresponding joint distribution function of this random vector. Now, what we are going to see are results which are exact analogues of what we have already discussed while considering the weak convergence in one dimensional setting. First, we start with the pointwise limit of distribution functions. The first result that we discuss is the Hellis selection theorem, and this is the d-dimensional version of the Hellis selection theorem, and we state it as the same under the same name. So, this goes as follows. So, we start now with a sequence of probability measures, call them as mu n. So, now all these probability measures are defined on R D together with the underlying Borel sigma field, and suppose the corresponding distribution functions are given as f n. Hellis selection theorem says that we can extract a further subsequence f n k and a non decreasing right continuous function defined on R D such that the limit values hold at every continuity point small x of the limit function f. So, here recall the notion of non decreasing properties, it is in terms of the non decreasing properties of the probability measures. So, you associate positive mass to all sets, and in particular we get it for all bounded rectangles, and that essentially is the non decreasing property for the underlying distribution function. Right continuity is also similar, that you have to look at essentially the joint right continuity in all the component variables. Alright, so this is exactly the analog of the Hellis selection theorem, and we do not go through the proof anymore. Now, as considered earlier, motivated by Hellis selection theorem, in one dimensional setting we looked at the definition of weak convergence. Now, we state the similar concept now in this d dimensional setting. So, we first start with a sequence of distribution functions and another distribution function f, which will play the role of a limit distribution function. So, we are going to say that this sequence of distribution functions converges weakly to this limit distribution function f if this limit holds at all continuity points small x of the limit distribution function capital F. So, the definition is the same definition that we considered in the one dimensional setting, we are just extending it to the d dimensional setting right now. And as done earlier also, we are going to use this notation to denote the weak convergence of these distribution functions. And as soon as you have the definition of weak convergence for distribution functions on R D, you extend this to first for probability measures by this, that you take these probability measures mu 1, mu 2 and so on R D and consider another probability measure mu. Suppose the corresponding distribution functions are given like this, then we say that mu n converges to mu in the weak convergence sense, provided the corresponding distribution functions converge weakly. And if this happens, we are going to denote this using our familiar notation that mu n converges weakly to mu. And once you have the concepts of weak convergence for probability measures, we also extend it to the case of random vectors now. So, here the idea is that you look at a sequence of random vectors which are now d dimensional, and let x be another random vector. Now, here while considering weak convergence of random variables, we have pointed out that the random variables, when you are considering the weak convergence, they need not be defined on the same probability space. So, here also if you are considering the extension of the similar ideas for random vectors, then again we can allow all these random vectors to be defined on possibly different probability spaces. So, let us see the definition. So, what we are now saying is that suppose capital X is defined on omega f p, x 1 is defined on omega 1 f 1 p 1 and so on. So, we are going to say that x n, the sequence of random vectors, converge weakly to this random vector x, provided the corresponding laws converge weakly, and this essentially means the corresponding weak convergence of the associated distribution functions. So, this again the basic idea is that you first start with the notion of weak convergence of distribution functions and extend it to the collection of probability measures and the random vectors in the d dimensional setting. Now, as done earlier in the setting of random variables, the weak convergence of random vectors, we will also refer to them in terms of convergence in law or convergence in distribution. So, we are going to say that x n converges to x in law or x n converges to x in distribution. Now, again we have encountered this concept of tightness while talking about the fact that how to ensure that a limit function for a sequence of distribution functions is a distribution function on its own right, and there we encountered the concept of tightness when we were discussing this situation in the one dimensional setting. Now, a similar result goes through when you are looking at Borel probability measures on R D. Again the tightness is defined in an exact similar manner, but we are not going to discuss this concept in the higher dimensional setting in this course. Again we continue looking at the corresponding statements that we have obtained in the one dimensional setting. So, we just state them, we do not go through the proof because the proofs goes in the exact similar way. So, in theorem 3 of week 6 we had listed a huge list of equivalent conditions for weak convergence of probability measures. So, let us set up the notations. So, we are going to work with this sequence of probability measures and let us mu denote the corresponding limit measure. So, the idea would be that you work with the corresponding distribution functions. Now, if mu n's converge weakly to mu equivalently in the sense of corresponding weak convergence of the associated distribution functions, then this is the first condition that we state. So, this is essentially the definition that we are considering. But now, as considered in the one dimensional setting, we will look at integrations of some nice class of functions. So, if it so happens that for all bounded and continuous functions f defined on R D and real valued functions, if the integrals of f with respect to mu n converge to integration of f with respect to mu as n goes to infinity, then this is equivalent to the weak convergence of the corresponding probability measures. You can further restrict this class of functions to be only bounded and discrete continuous. Moreover, you can also choose to look at special type of subsets of the R D and look at, for example, all open sets. Then the condition in terms of all open sets come in terms of this inequality that lim of mu n of g has to be greater or equals to mu of g. A similar condition in terms of closed sets looks like this, that you have to have the lim sup of mu n of f should be less or equal to mu of f. And finally, the equality should hold if you are working with mu continuity sets. So, that is this statement here. And we state one more condition now in terms of the corresponding characteristic functions, that the corresponding characteristic functions must converge pointwise sense. All right. So, if this happens for all points in R D, then we say this condition is equivalent to the weak convergence of the underlying probability measures. So, again this last statement is essentially the Levy's continuity theorem that we have seen in one dimension. So, the exact analog in d dimensions also go through. All right. So, now with this understanding of weak convergence of the probability measures, we can further state the conditions specifically for the weak convergence of random vectors. So, in the case of random variables, we had stated these conditions which are useful in practice. Now, we see similar conditions being stated for the case of random vectors. So, let us see. So, we take these random vectors, let us say x 1, x 2 and so on, forming the sequence, and suppose you consider x to be the limit random vector in the sense of weak convergence. So, we are saying that the corresponding distribution functions converge weakly to the distribution function of x. So, then the equivalent condition in terms of the corresponding expectations are like this, that you are going to consider all bounded and continuous functions on R d and look at these random variables f of x n. Look at the corresponding expectations, these expectations should converge to expected value of f of x as n goes to infinity. So, this is an equivalent condition. And finally, sometimes we are also going to look at the corresponding characteristic functions of these random variables, and if the pointwise convergence holds, again this condition will be equivalent to the weak convergence of these random vectors. Finally, there is this sufficient condition that we have discussed for the case of random variables, and a similar result is also true in the case of random vector. So, suppose you consider absolutely continuous random vectors, meaning their distributions are given through certain joint PDFs. So, suppose you have these joint PDFs associated with these random vectors, then if it so happens that for Lebesgue almost everywhere you have this pointwise convergence of the associated probability density functions, then immediately this will be implying that the corresponding random variables converge in the weak sense. Remember, we have seen such a result in the setting of random variables also, and in fact, as a consequence of this result, earlier we have talked about the convergence of Gaussian random variables. So, we now consider an example in the two dimensional setting. So, we are talking about certain normal random vectors now in the bivariate case. So, let us say we consider a random vector with components x y following normal distribution bivariate normal with mean 0 each and with this variance covariance matrix. So, in particular you will immediately say that x and y individually are standard normal random variables which are also independent. So, that follows from looking at the covariance structure here. Now, look at another sequence of bivariate Gaussian bivariate normal random vectors given by this, that these means are 1 by n each, and suppose you consider the variances like this and the covariance structure given like this. So, then again if you let n go to infinity, you can look at the corresponding characteristic functions for example, and justify the pointwise convergence, and you will immediately have the weak convergence of this sequence of bivariate normal random vectors converging to this random vector x y. So, again the calculations remain exactly the same as we have already considered in the one dimensional setting. Nice application of the conditions that we have derived so far. Now, we go and look at an important understanding of the weak convergence in the d dimensional setting and the one dimensional setting. So, this is a important identification that reduces the complexity of the problem in the d dimensional setting to one dimensional setting. So, to do this we require certain notations which are something familiar that we have already seen. So, if you pick two vectors u and v coming from R d, we know about their dot product, which is also the standard inner product in this Euclidean space, which is also u transpose v, which essentially means this summation of the product of the components, and then you look at this summation, right. So, that is the standard dot product which is there in R d. Now, we are going to use this to reduce the weak convergence problems in the d dimensional setting to the one dimensional setting. and this result is typically referred to as the Cramer-Wold device or the Cramer-Wold's theorem. So, the idea is like this. We are going to consider the weak convergence for d dimensional random vectors. So, suppose you have a sequence x 1, x 2 and so on converging weakly to a random vector x. Then this happens if and only if you look at these projections along the direction of all vectors u. So, essentially we are looking at u transpose x n converging weakly to u transpose x. Note that u transpose x, if you look at it, this is now a real valued random variable, which is essentially made up of the components u j x j as j goes from 1 to d. So, here u j is basically playing the role of the coefficients in this linear combination of the component random variables. So, what we are essentially saying is that you look at all possible linear combinations of the component random variables, and we must have the weak convergence for all such linear combinations. So, here that is why the u plays the role of the coefficients in this linear combinations. So, let us see the proof. So, we start by assuming that x n, the sequence of random vectors, converge to the random vector x in the weak convergence sense. Now, fix any u in R d and also fix a scalar alpha in the real line. Now, by our earlier understanding, we are going to look at these vectors alpha times u, this is in R d now, and as soon as we have said that x n's converge weakly to x, this is equivalent to the pointwise convergence of the corresponding characteristic functions. We just evaluate them at these vectors alpha times u. Now, you see, let us write down the expression for the characteristic function of x. This is the expectation of exponential I then alpha u transpose x. So, that is the expression that you are going to get. But now, you can revisualize this in terms of the random variable u transpose x. So, u transpose x is now a real valued random variable, which is a linear combination of the component random variables. So, therefore, we can write it in terms of the corresponding characteristic function of the random variable u transpose x and being evaluated at the point alpha. So, we simply rewrite our earlier condition of the pointwise convergence of the characteristic functions of the random vectors in terms of the pointwise convergence of these special class of random variables, and these convergence holds for all u in R d and for all alpha in R. Okay. So, if you keep your u fixed, then this is true for all alpha in the real line, and therefore, you are saying that the component random variables, if you consider this kind of linear combinations, they must converge weakly to u transpose x. So, therefore, we have proved one direction of the result. Now, conversely, suppose that all such linear combinations of the components converge weakly to x. Now, if that happens for all u in R d, then again we go through the characteristic functions pointwise convergence. So, we look at the pointwise convergence of these random variables at all alpha in the real line. But then as discussed earlier, this can be rewritten now in terms of the characteristic function of the random vectors evaluated at alpha times u. But if you choose alpha to be 1, this just gives you the pointwise convergence of the corresponding characteristic functions of the random vectors x n to the characteristic function of x, and hence we just appeal to the d dimensional version of the Levy's continuity theorem and immediately claim that this implies that we have the weak convergence of the random vectors x n to the random vector x. So, in this lecture we have seen the exact analog of the weak convergence that we have considered in the one dimensional setting, and what we see here is that all the results essentially go through with appropriate notational changes. So, you have to consider the d dimensional analogues and put in appropriate notations, but then all these results, all the equivalence statements, all the sufficient conditions that we have seen goes through with appropriate changes. And finally, we have also seen this very important theorem that connects the weak convergence of the d dimensional random vectors with the weak convergence of the linear combinations of the component random variables. And once you are looking at the linear combinations of the component random variables, you actually end up looking at weak convergence in the one dimensional setting, thereby reducing the complexity of the problem. We are going to see further applications of this Cramer-Waltz idea when we later look at further applications of weak convergence in higher dimensional setting. We stop here. Thank you.